Okay, so let's start the session. So this session will be mainly discussing. I will be starting with an intro about leg robots. Okay, not in deep, but just some idea. We will discuss, and then we will see some interesting projects, ROS projects in leg robotics. So that is the intention. I'm not I'm not discussing any theory of it, but some of the prominent projects that is done, um, yeah, that is already available in GitHub. Okay, and some major projects. That is what my intention. Okay, so you will get an idea like how to work with leg robots in ROS. That is the main intention. So I will be starting with an intro of leg robot. So let's start. Uh, I'm pretty sure that you have all seen the Spot robot from Boston Dynamics, right? It's a very popular robot. I hope you may see the Spot robot from Boston Dynamics. Yes. So this is the robot. I hope you have seen it. Maybe if you are not seen this before, maybe I can also play some videos to get an understanding. This is the structure of the robot, and it's a four-legged robot, by the way. And I'm pretty sure that you heard about the Boston Dynamics as well. Okay. So you know about this, right? Let me play a video as well, so to get it clarity. Just a second. Okay. So this four-legged robot, the main application they are proposing is that the inspection. Okay, inspection. You can see it is more like a dog, a robot dog, we can say, kind of robot dog. And the first thing I need to discuss is that we actually we have seen wheeled robots, right? Wheeled robots. We have seen the robotic arm. So why we have to switch, or why we have to plan for a legged robot? Are you seeing any advantage? So that is the first point we have to discuss. Why legged robots? I think you may have some idea, but maybe I can clarify that. So maybe after this video we can discuss about it. So why legged robots? Why not wheeled robots? Okay, that is one thing. So why the legged robot got or become popular? Okay, so let's see the video first. So the video shows it is going through stairs. It is going through industrial environment. On the top there are some very heavy sensor, okay, for mapping, and yeah, so very heavy sensor, and it can go through any kind of terrain. So see, like, it can go to like very rough terrain, then it can go through these kind of environment. No, it's very difficult to navigate. Okay, and I also talked about the Darpa challenge, right? The subterranean challenge. So this robot was mainly using to explore mines and all. So just check how good it is, how useful it is, because maybe after this video, let me just take some pictures. Okay, so this is the thing. Imagine if we are working with a wheeled robots. Okay, wheeled robots. So one of the popular wheeled robot, husky robot. You may have seen this husky. Okay, it is from the Clearpath Robotics. It's a very famous company, robotics company in Canada. So this robot is actually designed for outdoor. Okay, it can go through harsh environment, but can it climb the stairs? No, right? If the surface is uneven, or like there are limitation, because if one wheel is having issue, or like uh, if the terrain is not very flat, then it can have issues, right? So that is where the advantage of leg comes, mainly for leg. So for two leg also, like for human, uh, we the stability is very very concerning, because our brain can process the stability algorithm, or the balancing algorithm in our brain without thinking about the balancing. But for a robot, it's actually different. Okay, so there is one company called Agility Robotics. So it's also coming under the legged robotics, but it's two legged, okay, biped. So you can see here uh, the latest update from this company is this robot participated in some marathon or some sprint. Yeah, it actually showed that it can able to run. Okay, so this is the first prototype, I think. First prototype they are using for the training. Biped. Yeah. So it's also an interesting development. Why the biped is actually delaying? Because biped is difficult. Okay, biped is very difficult. So you may be thinking like the Asimo robots, Asimo robot. So that's also a humanoid robot, right? It's not. Yeah, this one. So a humanoid robot. Yeah. So this is also a very challenging project. Okay, it's a legged robot, two-legged, like human. So they also did a lot of research on this, and but this robot, no, this robot's basically biped mainly, focusing not a humanoid. It's mainly having that two leg, and we can put some payload on the top. Okay, so these are the interesting works going on, like the sport robot, then the agility. All these things are like currently going. But the main difference you can note between the wheeled robots and this legged is that the flexibility. Like if you watch this video, you can find it is going anywhere. It is not having any limitation. But if you put the robot in some very harsh condition, if it is a wheeled robot, then I don't think it can easily move. Okay, so the movement is one thing. Okay, so there are many advantages for leg, especially in difficult terrain. That is, I think, one of the reason why the wheeled legged robot got popular. But before that, if you check, most of the research works was in the wheeled robots. Okay, still wheeled robots are using, for example, food delivery robot. Okay, food delivery. So in that we are using wheeled robots only. Like if you check um, this robot, no, you can find it's six-wheeled, and yeah, it can go through this like roads and all. It is fine, but again, like there are limitations. But for this particular application, maybe it may be fine. Okay, yeah. And some of the advantages of wheeled robots are like, if you check the Sport Mini or Sport, uh, there is obviously some speed limitation. Okay, it can run, the Sport can run, but there will be some speed limitation compared to wheels. Okay, yeah, but the problem is that again the cost is one issue. So the Sport robot cost around 75,000 US dollars. You can imagine 75 K USD to INR. If you just convert into Indian rupees, it is around 61 lakh. No, it's not 61. Yeah, I think so. Like $1 lakh is 80 lakh roughly. So a single robot cost around 61 lakh. Okay. And this robot, no, this robot Husky is cost around, if you import to India, for example, it's cost around 30 lakhs. So, I mean, this robot's also costly, but if you check the sport, it is much more expensive. And especially if you import to India, then there is a tax. So it will be like 60, 75, almost $75,000 to 75 lakhs. Okay, so for the single robot, so it's very very expensive. So that is one concern. But if the production goes on, if there is a mass production, I think the costing can be reduced. Okay, so this is for the standard robot, one of the standard robot available, but there are cheaper legged robots available. So Unitree is one company, Unitree Robotics. So like nowadays, like a lot of companies are popping up with their legged robots. Even Xiaomi, I think, Xiaomi robot legged, Cyberdog, yes, this is Cyberdog, yeah. So this is the robot from Xiaomi. It's actually, Xiaomi is a mobile, the smartphone manufacturing company, but they are also going in other verticals. Okay. Yeah. So yeah, Rohan is having a comment. Like, I guess the dog frame is chosen because dogs perform many roles, humans such as exploration. Yeah, yeah. That's also a thing. So it feel like a pet, right? So that is also a thing. But moreover, the functionality wise, it should be useful, right? Even if it is a biped or a quadruped, if you choose any shape, it should be useful. So the Unitree robot, as Rohan mentioned, it looks like a pet. So this is Unitree, and it's much, compact compared to the Boston Dynamics Sport, and it is also having a lot of things. I mean, if you are looking for a research, I think it is having the main sensors that we want. Then the walking algorithm is okay, and it's also portable. It's not very very heavy, I think, compared to the Boston Dynamics. And there are multiple models as well. Okay, so that is interesting, and they also showing some example that can compete with Boston Dynamics. So here you can see different models. Yeah. So the Tejas is having a question: how does the kinematics differ from differential drive? So Tejas, the differential drive basically, it's adjusting the speed of two wheels. Differential drive, it can be two wheels or like four wheels, but basically the logic is that if two wheels is having same speed, it will go forward and then backward, something like that. So here, instead of adjusting the wheel velocity, it is having the gates. So if, like, in some way, the concept is almost the same. Like, we can go forward, we can rotate, and in sideways also, I'm not sure, but maybe it is almost compatible with the differential drive, because why I'm saying is that this can be easily integrated to the navigation stack by putting an extra controller. So the main difference is, instead of having two wheels, it is having four independent legs to control, and there are some other difference, like it can move in y direction. So you can see the robot can move in x and y direction, so like the omni wheel. So we can compare this as omni wheel robot, like using the mechanism wheel. I think we can compare with that. And yeah, so these are the similarities. Okay. But it's very easy to control. Only thing is that the main challenge in leg robot is the coordination of legs, and also not only that, like simple walking is not enough. Like if the robot falls or a robot is pushed by some external force, it should balance that. So these all are the challenges. Okay. So unit 3 is one of the compact and also cost effective robot. You can see it is like 2700 USD. So it's much cheaper than, like, for Boston Dynamics it was 75k. Unit 3 is 2700. So compare these two models, it's way cheaper. But again, we can't compare the quality and also the payload. Payload will be like less compared to Boston Dynamics. And another reason is that it is manufacturing in China, and Boston Dynamics, I think they are doing mostly in US. Okay, so Unit 3 is a Chinese company. Yeah, so that is one. And the CyberDog is another interesting robot. I think there is some interesting videos. Let me check. Yeah, I think there are some video released by Xiaomi. Yeah, like the dog, they are, that is the easiest way to market, right? Like your pet dog, there is a robot dog. So this is how the cyber dog looks like. So I like this design actually. It's pretty good. I'm not sure it is original or the rendered one, but I think the design, yeah, I think it's the original one. I have a doubt because that is not very easy to do. Anyway, like you can see the design. It is slightly interesting. Better than the Unit 3. So I will say it will be in between Unit 3 robotics and Boston Dynamics. And the cost wise also, I'm not thinking like it's very high. Yeah. Yes. So from my opinion, like they're also like open source the code. Yeah, that is again a good thing. So it's an open source robot. I think that is also mentioned in the GitHub. Let me check. Cyber Dog 2 GitHub. Yeah, this one. So we have the ROS 2 packages for the CyberDog, so you can easily program it. So that is a good thing. Mainly we can use it for the research, and a lot of people are like starting it, so that means people are using it. Okay, people are using it and you can easily install all this stuff. Yeah, that's interesting. Yes. So these are some of the example for currently like the available quadruped robots that we can buy. I'm not sure CyberDog is available for purchase, but Unit 3, yes. Okay. So the main difference in Sport is that it's very very sturdy, and also it can carry a big payload. So you can see here there are LiDAR, Velodyne, then on the top there are some mapping tools. So in order to handle all this stuff, it has to carry, it should have the payload, very high payload. So you can also see Sport robot in the subterranean challenge. Subterranean. Yeah. So actually NASA, the JPL team, they actually participated in this competition, and they have a series of the team name was Costa, and they have a series of robots. So you can see Husky here, Husky robot, and they have the Spot. Okay, and you can see the list of sensors that is mounted on the top of the robot. Okay, so you can see like we can mount a lot of stuff. This is a kind of drone. It can move through the floor as well as it can fly. Okay, so these are some of the images that is taken during subterranean challenge. So you can easily see these kind of robots are using in this very complex environment. Okay, yes, yeah, so that is it. And I just want to see, I just want to show the some video from Boston Dynamics. After that we can jump into the ROS part. Just a second. Boston Dynamics all videos. If we can see, we can find some interesting big dog. Yeah, so this is the evolution, guys. I just want to show you the evolution. So the research that is doing by Boston Dynamics is started like, see, this video posted before 12 years ago. So you can imagine these guys are like researching years in order to create a very stable and a viable product. So this was the old prototype, but it will work perfectly. You can see it's kind of yeah, it's a forest, right? And it looks like two people are walking front and back, and you can see the person is pushing and the robot is balancing. So this is where the complexity comes. Even walking is a challenge, that I agree, but this kind of balance, see, there is an ice on the road, and this is amazing. Actually, this is an amazing section that you are seeing. Like the legs are like slipping, and like human, it's trying to balance. Amazing, right? See, it's trying to balance. It's not falling down. Okay, so just imagine the work they have done before 12 years. Okay, and this robot, this robot dog, or called the big dog, it's not using electronics in the sense electronic actuators. It's mainly using hydraulics. Okay, hydraulic and pneumatic. So the control will be much difficult than like control of like BLDC motor or some DC gear motor. Okay, so it is having an engine, hydraulic engine, and yeah, so that is controlling by a computer. So it's, I can't believe this kind of work. It's quite amazing. So maybe we can actually take inspiration from this. Yeah, so Tejas is having a question. Oh, there are two questions. One from Rohan. Are they using kinematics like universal robots? So the kinematics side, yeah. So each wheel, each leg we can consider as a robotic arm mounted invertedly. We can consider like that, but the the Boston Dynamics, I don't know, they have their own algorithm, but we can treat each leg as each robotic arm, and then we can plan. So using move it, we can actually control a quadruped, or we can write a controller which can control the robot speed by adjusting the gait pattern, leg gait pattern. The moving pattern is called gait pattern. So if you just search for gait in quadruped, it's actually the that movement is basically called the gait, walking gait. Yeah. So so we can control the robot in any method. Okay. And Tejas is having a question: is it fully embedded? So yes, Tejas, like there is no wires. Everything is on the robot, like including the hydraulic actuators, which is using in the legs, then hydraulic engine, like the JCB. You have seen the JCB, right? The JCB. So it is having the hydraulic actuators, and there is a hydraulic engine. So like this robot is designed, and it is fully embedded. Everything is inside the robot, and it looks like two people are working, right? So yeah, so this is actually the evolution. And also there are some other robots. Maybe I can show you that. This one actually amazed me. Okay, so and MIT Cheetah, you may have seen this one as well. There is a video actually. This is also in association with Boston Dynamics. I think they have I think the founders of Boston Dynamics, they are having tie-up with MIT, and in an MIT lab they are working on quadruped. So this is like it is testing the speed. Like the name of the robot is MIT Cheetah. So the intention is achieve the speed, maximum speed. I don't think we can achieve the speed of Cheetah, but still, as much as they can do, they are actually training. So you can see here, it's amazing. Another video they published before 7 years. Okay, it's actually jumping, and it's not easy. You guys already know, right? See, it's very difficult, and this is also, I think, not using BLDC motors or something. It's all hydraulics. So there will be sound. It's somewhat noisy because we have to run the engine. Yeah. So these are the works that happen before. The spot, and they have some MIT mini Cheetah as well. This is mini Cheetah. They released before 3 years. It's interesting. It looks like Unitree robot. You can see here. I think the Unitree may be inspired from this design. It seems like exact replica, okay, of MIT Cheetah. Yes, they may hire people who work with this project. That can be, but this is like the BLDC. It's an electronics, completely electronics. There is no mechanical, not mechanical, hydraulics or pneumatic actuators. But it is doing the job. Like, even it is small, it is almost doing the same thing that see, it can also recover. So these kind of behavior, we have to model. Yeah. And landing, which is commonly seen in cats and dogs. So yeah, that it can do. And backflips. Oh, interesting. Yeah, very nice. Yes. Yeah, so I think you got some example of the quadruped robots, right? MIT Cheetah, then the latest one is a Sport, and Unitree, then Xiaomi, Cyberdog, all these things. And there are some cool projects, small projects available, which is completely working using ROS. Smart mini, okay. Sport micro. So these all are like small projects. You can also build these projects, mainly done using ROS. So this is one Sport Mini. Maybe I can share the link. We will be seeing the code maybe. Yeah. So mainly prototyped using servo motors, and they're also using the OpenAI Gym framework to train it. So that is interesting. And yeah, yes, this is one project, and one of the other project is Sport Micro. This is again good because it is inspired from again the Sport robot, but a little better than the mini I will say. And there is another, yeah, Sport Micro, yes, this there is another one. I mean, there are a list of projects that is inspired from the Sport robot. So the Rohan is having a question. So are they using AI? So here, uh, in the Sport Mini, what they are doing is there is a thing called OpenAI Gym. Okay, I can show you that. Can you see this environment? This environment, yeah, yeah. So yes, yes, exactly. So as they just mentioned, it's reinforcement learning. So in the OpenAI Gym, they are training the robot using the reinforcement learning algorithm, and then after that, after training, we can test that robot, test that simulation. I mean, using that value, we can feed that value into a real robot and it will work similarly. So it's actually based on this kind of training, reinforcement learning. Okay, so but it seems like all these project, no, all these project they are actually using ROS. Okay, mostly they are using ROS. Yes. So these are the interesting small project. If I miss anything, I can mention. Yeah, and one of the popular project is Champ, which is again very popular. Like the Linobot, right? Linobot project for wheeled robots. So Champ is actually done by Linobot author. His name is, I mean, the GitHub ID is Grass Jelly. So he created Stack. I mean, this repository which is having multiple robots. Okay, so you can configure which robot that we want. Okay, and we actually missed one more robot in the quadruped called Animal, which is again a popular robot. There is a company called Anybotics, which is in Switzerland, in Zurich. So one of my junior working there. So he's one of the engineer who developed the Animal robot, and maybe we can see that also, which is a direct competitor for Sport Mini or Sport robot from Boston Dynamics. Let me try to load this. Yeah, this one. I'm not sure you have seen this robot, but it's also very popular. So there is a quadruped robot lab in University of Zurich and the ETH Zurich. Okay, so the Animal or Anybotics is actually a spin-off from ETH Zurich. So you can see it's doing the same thing like Sport, but I'm not sure about the cost. Maybe yeah, yeah, they didn't mention the cost. Maybe it may depend on the uh, solution they are providing. So maybe we can see a animal robot video and then directly go to the project. Okay, the list of quadruped robots. So this, I think he's a CEO of animal. See, there, I mean, the sport and animal are in the same domain, the same business domain. Um, they are mainly using in surveillance and monitoring. Uh, yeah, especially in very riskier environment, because recently I got a project. I mean, it's a project inquiry that they are looking for a robot which can work near to the furnace. Okay, near to the furnace. Furnace means like, right? The environment will be very hot. So it's very risky to go there near to the furnace, but somehow they have to manage some valves or something. If there is if the temperature is in some with limits, then it has to close or something. So in this kind of environment, robots are a very good solution, because we can control the robot from the base station remotely, and then the robot can do the job. And also on the top of this robot, we can mount a robotic arm so that it can do some manipulation. So here also you can see in animal, there is a lidar and there is a place for putting the payload. So very similar, but the technology wise, these two robots are different in the sense, the algorithm wise. So these two robots are developed the technology independently. In the front there are camera, on the side also there are camera. Yeah. So this is one popular robot. You can see the mapping of, that's interesting. It is collecting the data around the robot using the lidar and the depth camera, and it can path plan based on the environment. Yeah, so you can see it is creating a 3D map. So yeah, this can be used for creating the 3D map as well. Like, you can simply move the robot around the industry, and then it can get get back to you with a 3D map. Okay. Yes, and also we can put many sensors like thermal camera, lights, anything for the inspection. Okay. Yeah, so these are some use cases they have done. I think it's inside a ship. So they have put a thermal camera or something. Yeah, and they have to, the robot has to monitor the valve or the pressure reading and all. And then yeah, so this kind of monitoring is we can do very effectively using these robots. Okay. Yes, so that's it, an intro to the quadruped robot. And in this chapter we are focusing on the ROS side, so we can quickly jump into the ROS part of it. Okay, so let me close it and let me start with the projects. Okay, so first we can start with the project called champ. Okay, so before that I just want to show you the relevance of ROS in quadruped. Okay, just a second. Okay, ROS computer setup, melodic. Yes, so you may be thinking like ROS may not be using in sport or something, but the thing is, ROS can be used in this robot. They are providing the option to install ROS on the spot. So this is the instruction. Actually, for Boston Dynamics, the spot driver actually created by ClearPath Robotics. Okay, because ClearPath Robotics is one of the pioneers in ROS. Okay, so you can see the instruction that we have to do in the spot robot in order to work with ROS. So I think the people from JPL or NASA, they have make use of this driver. Then then we can easily work with ROS. Okay, so this is one thing. So you can also see in the ROS website that the spot is supported by ROS, and the driver, the main driver is the part where it is communicating to the robot. Okay, so if you want to control the robot, then we have to start the driver, and the driver will be sending the command to the main controller. So the controller is controlling the robot. Okay, and also it is giving the sensor data from the robot. So here there's a video with the ROS packages. So you can see this is RVs actually, this one. Okay, so this is actually the visualization that we are getting in RVs. So 3D visualization. Okay, so using this driver we can able to interact with the spot. I just want to show you some yeah. So this is another visualization coming. See, so the robot is moving and we are getting the data. This is from the LiDAR, and also there are depth cameras. So using this sensor data, we can easily control the robot. Okay, so yeah, I think it's also on the left side you can see the camera. There are multiple camera, monochrome camera and RGB camera. So we can make use of that sensor. There is a router on the top. It's a dedicated computer. So basically, what you have to understand is that controlling using ROS means inside this robot, the main code will not be using ROS. That is the proprietary algorithm. Main code in the sense, if you provide some velocity commands, for example linear and angular velocity, to the main controller, that is the proprietary part. They will not open source it, or they will not disclose it, because that is their research work. I mean, you have seen, right, the evolution of the robot dog. It's actually like 15 years of work. So that is the core part of this robot. So they will not disclose that. The source code is proprietary, and what we are working is on the top of that layer. So we will not get access to that code controller part, but we can give the robot the commands, so that like if you send a linear velocity, it will maybe moving forward. If you give the angular velocity, it will rotate, something like that. And also we can set the join values. Okay, so that is the ROS layer. Okay, so the sport driver means, the ROS driver means that driver can interact with the low level embedded controller that can move the robot. Okay, so here you can see there is a, on the back side there is a computer with Wi-Fi, and then yeah, I think it's sensors like IMU, all this stuff. Yes, and we can build any sensor on the top. Yes. Okay, so that is the driver, latest driver, and if you check the animal, I think it's completely done in ROS. Okay, so you can see the entire research that they have done. They mainly make use of the open source software, I think. You can see here. And yeah, so these are some of the ROS related packages they have open sourced. Okay, but the main code, I don't know, like it's still not open source main controller code, but they have open source lot of ROS related stuff. Okay, yes, okay, but we are not going to see the code of sport driver or animal. What we are doing is we are looking for some projects, like some interesting hobby projects, okay, so that we can test it on our machine, and yeah, we can do the simulation and all. So the CHAM project, I think I have shared the link, right? Maybe I can share it. You can have a look. This is a quadruped robot project, and you know the Lino board, right? Lino board. GitHub. This one, right? This is also very popular. Like it is for the differential drive robot. It's one of the reference project. Yeah, the same author gradually actually created CHAMP. Okay, and the CHAMP is also available for ROS 2. Linobot is also available for ROS 2, and it's very easy to configure. Seems like he tested on 18.04, but it will work with Noitic. So simply follow this instruction. Just that you need to do, and build your workspace, and then you can run the driver using RVs, or you can simply start the simulation in Gazebo. So I have set this repository in my VMware. So can I run it? Maybe I can show you the simulation. Okay. So I have the simulation for the sport as well, but there are some problem with the movement. I can show you that as well. Okay. So first, let me show you the CHAMP robot project. Okay. So let's see how that works. Okay. So this is the environment they have created, and here is the hobby robot. Okay, you can see here the robot is having a laser scanner on the top, then it is having a depth camera on the bottom. Okay, and we can see how to move it first. Okay, like a wheel robot. So we have started the simulation, and then let's try to move it. So let me check the command to move the robot. So here there is a teleop here I've created. So just starting the teleop, and using the keyboard we can control it. Okay, just a second. Yeah, so we have started the teleop, and now let me control it. If I move it, you can see the robot is slowly moving. Okay, just a second, getting a message. You can see it is rotating. Yeah, yes. It's actually slow, but it's doing the job. It will take some time to rotate. Even if you press the keyboard, it will take some time. Okay, maybe we can increase the speed slightly. Let's see whether that works, but still it's slow. Okay, so this is one reference project that you can take. Yeah, and but interestingly, he have done more works in this project. Maybe I can show you that. We can see how we can do the mapping navigation. Just a sec. So let me start the simulation, and we can see how the mapping is doing. Oh, copying. Okay. Yes, simulation. Okay, now I can run the slam. Okay, I think it's the G mapping or something. Let me check. No, it's not G mapping, it's Hector slam. So I'm starting the slam. You can see around it, you can see the laser scan. Robot is here. It started creating the map, and I can move the robot using the keyboard teleop. Let me see. Okay, so let me start moving the robot using the keyboard. You can see the robot is slowly moving. The laser scan is also changing, and you can see the map, underlying map is creating, but there is a problem. There is an obstacle. You can see it is creating when the robot is moving. Okay, maybe I can explain it after some moments. Okay, let me rotate. Yeah, so the problem is that if you can see the robot, you can understand the problem. So here is a robot. Okay, here is a robot, and when we move the robot now, you can see it's like the sensor is putting on the top of a horse or a cow. Like the sensor is like some kind, it's not very stable. It's keep on tilting its pose. Okay, so that's why you can able to see a tilt in the laser scan. Okay, it's like wobbling. Okay, so this project is not perfect, but you can able to see like it is creating the map, and yeah, so using slam it is working. Okay, so that is actually the slam launch file is doing. It's doing, like you can see the map is creating on the back. Okay, so after mapping you can save it, or if you want to directly want to test the navigation, you can use this command. So the map is already built. You can simply start the navigation launch file, and then you can give the goal position and it will work. Okay, so can we try? Maybe we can try that. So first, starting the launch file for simulation, and okay, so the robot is here. Now the navigation. So you can see the map is popped up, and you can also see it will take some time to yes, it's actually created the layers like global course map and local course map. Now is the time to give a goal position. Like I'm just giving a goal position here, so you can see it's planning a path. But the problem is this is a global path, like the navigation stack. This is the navigation stack only. So here you can see an obstacle, but in reality there is no obstacle. So this is happening because the laser is wobbling, and it is assuming that there is an obstacle in the ground. Okay, so that is what this problem. Okay, this problem, maybe he can fix it, but I think there is no. So the problem is that when the robot moves now, it is detecting an obstacle and it will be moving away from that obstacle. Okay, but in reality there is no obstacle, so it will be like in a trap. So that is a problem, but we can easily fix this issue by tuning the navigation parameters. Okay, yeah, so this is how the navigation works. Like if you give a goal position, it will be, yeah, so same as the wheel robot, little bit slow, but still it works. Okay, yes, okay, yeah, it's not very very fast that you can see. Yes, so this is navigation. You guys can try. It's very easy to set up. Yes, okay. So after this project, I can simply show you the sport simulation, sport mini, not sport mini, sport robot simulation. After that we can conclude. Okay, just a second. Let me take that. Soft serve. Okay. So this is one repository that I got for simulating the sport robot. It's not very perfect, but you can able to see the robot working, and I can simply show you the simulation. So this will be like showing the simulation of a world. Yeah, so this is the world file, and then we are, they have another launch file to spawn the robot. Okay, so spawning the robot. So this will be spawning the robot in the world. You can see here is our sport robot. Okay, so we got a 75k US dollar robot in our simulation. Okay, it is interesting because you can play with the robot without spending any cost. So that is the advantage of working with the simulation. Okay, yeah, so after this I got this command working, but not the teleoperation. I will check that maybe tomorrow. So when I'm trying this, it seems like it's executing some motion. You can see here. Maybe I can delete the world. Yeah. Yeah, it's still good. I mean, it's balancing and it's working good actually. But I couldn't test the teleoperation. I think that we can easily do, but there are some issue with uh, the controller. Yeah, so this is one simulation. Maybe tomorrow uh, I can move the robot using keyboard. There are some instruction, but let me check. Okay. Okay, so that's it, guys. So today we have discussed some basic stuff, and we have seen two projects. Okay, so if you have any question, let me know. And tomorrow we will be continuing with this, and then we can jump into some other topics if we can. Okay, so any question, guys? Do you have any questions? Any questions? So we have seen the champ project, sport robot, then mapping localization, and we can see some hardware things. And then there is a project called Open Dynamics that we can see tomorrow. Any questions? If you have any question, then okay. So there is one question from Tejas. They have APIs available. Okay, I think yeah. So for Boston Dynamics, they have APIs. There is an SDK, so we can make use of that SDK. So the driver, the sport ROS driver, is making use of that SDK. Yes. So that's how it is working. Any more questions? Okay, I think that's it. So we can conclude today's session. Thanks for attending. So tomorrow we will be discussing the open dynamics and the construction. Uh, yeah. So Tejas, yeah. So this is going to be the next chapter, the projects. So hopefully I can send, or we can discuss. I mean, this is going to be the next chapter. Okay, so maybe tomorrow we can start with the project list, Tejas. So we can discuss some projects from my book, and then yeah, we can discuss. Yeah. Okay. So this is the next thing. Okay. Okay, guys. Thanks for attending. See you tomorrow. Bye.